I think we will start to wrap this up. And of course, you can keep developing, like working on the solution after this session. Anyone have any suggestions on how to solve this dreaded int pointer problem? Yes.
So the arrow to constructor of iterator range from iterator range is iterator type, which is compatible with the iterator class, with the iterator type used in the class being constructed.
Correct. Very good. So I rephrase it. Iterator range should be constructible from an iterator range whose iterator type can be copied into the target iterator. You have two iterator ranges, one of it1 and the other one of it2. As long as you can copy it2 into it1, you should be able to copy iterator range of it2 into iterator range of it1. And this is exactly the relationship you have between const iterators and iterators. And it makes sense. That's why I said, think of it as this thing is a pair of iterators. What can you do with a pair of iterators? Well, you can copy this one iterator into the other iterator, and it works. So you should be able to do the same thing with iterator pairs. It's just a thin wrapper around iterators. Okay? So this is exactly the right idea. Let's talk a little bit about other aspects of the solution. And these are kind of these things that actually you have to think about when designing a library. And often it helps to kind of step back from the concrete case and think, how is the world supposed to be like? Right? Look at it from a philosophical perspective. And it often helps to find the right solution for these problems so you're not all over the place fixing special cases and it comes out at the end, it comes out of your ears, right? So here is your iterator range solution. Yes, you can construct an iterator range out of two iterators, but you also have this thing. You can copy at the bottom, you can copy an iterator range out of another iterator range. How do I have? Here we go. Out of another iterator range, as long as these two are actually copyable. Okay? As long as you can copy the iterator into the iterator, you can also copy the iterator range into the iterator range. And that solves nicely your problem because you can actually construct the iterator range int const pointer from the int pointer. Not the other way around, but that way around you can, and that's exactly what you need. And that solves nicely your problem. What are other things that you have to watch out for in your for each unique range? As I already said, you should take this thing by range ref because you want to pass to your functor, which you take by value, you want to pass as strong iterators as possible to that functor. Why do you take the functor by value? Well, this is kind of like a convention that's being used in the standard library. The for each has the same thing. If you call for each, the functor gets taken by value, so it gets copied before it gets called. Is that a good thing or a bad thing? Well, it's kind of the way it has always been. And it's not really a good idea. As I said, if you want to change something in the standard, it's going to be very, very difficult. So I would stick to that convention. What was the original idea? I think the original idea was that the functor may be very, very, very lightweight. For like doesn't exist at all. It's an empty struct. Okay? And an empty struct, if you write reference, is really underneath it is a pointer. And we don't really even want to pass a pointer. We want to pass nothing if this is an empty struct. And you can always write stdref around any functor that you want to pass by reference. But you can't unreference. If you actually decided in the signature to take by reference, you can't undo this decision. You can change it one way. You can make it a reference by write stdreference around it, but you can't do it the other way around. And I think that was basically the original idea when they actually came up with that design decision to pass the functor by value. What else do you have? There is the question here, first of all, unique. Runs with the iterator over the range, and then looks at the next iterator, and if the next iterator matches that iterator, it throws that one away, boom, and then it looks at the next one and throws that one away, boom, okay? What it doesn't do, keep in mind here, after you've thrown this one away, you keep the one that you compare to be the first one in your range. So you are hitting a new range, a new unique range. You keep that iterator there, compare the second one to it, the third one to it, the fourth one to it, the fifth one to it. You don't do this, bang, 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 bang. You keep the first one where it is, and then always compare this one to the first one, and the third one to the first one, and the fourth one to the first one. This may make a difference sometimes, okay? So you would like to exactly imitate the behavior of std unique. It was a bit unfair because you didn't have the specification of std unique in front of you, but that is the implementation. That is the specification of std unique. And when you're writing a library function, you have to be pretty tight-assed. You already noticed that. And this is one of these things that you have to be tight-assed about. What exactly is the comparison that I'm doing? Now, and then there is one more thing that we can think about. Should you dereference this thing that you are comparing against, the star it left? Should you compare it, dereference it every time? Or should you store this value? That's a bit of a difficult decision. If you worry that the following things, for example, could happen. It could be that your type that you are having there, that the star it left is passing out to you, it passes out a reference. What if the type's not movable even? It's not copyable, it's not movable. Oh shit, right? You can't even store that value. You can't put it into anything. No one requires that range that you pass in to actually have values which are movable. That will be an additional requirement on your values. And you may not want to make that requirement. So probably storing the value in a temporary variable and then comparing to that may seem more efficient, but generically it is possibly a bad idea because you may not be able to actually copy that element into anything. It may just sit there and you get a reference to it, but there's all there's to it that you can actually do. Okay. So that would be one thing. So here I would, the it left must be the beginning of the range. You probably don't want to store a temporary variable. I wrote the static cast bool in front of it. What is that about? Why did I write static cast bool? Anyone? First of all, well, I applied here the not operator, right? Well, what I'm requiring is that these two things are equality comparable. So you have an equal operator. No one tells you that you have an unequal operator. You have an equal operator. Please stick to your ass must be really tight. All right? So you have an equal operator. Now, could you directly call the not and then have this in parentheses? Well, what if this equality doesn't pass out a bool? It passes out something that has an overloaded not operator. Okay. Yeah, you must really watch out, right? Okay. You still want the algorithm to work. Okay. You only require the only equality operator. Everything else you don't know anything about. Okay. So you have to write it like that. The other thing that maybe what you're passing out here is something that doesn't have an equal, like a not operator at all. never mind, that's not a problem. You could have something here that doesn't, it has an explicit operator bool. There is something in the standard that's new that you can write explicit operator bool, explicit cast operators. And the explicit cast operator is not used for implicit conversions. So when you have an A and you want to pass it to a function that takes B and you don't say anything, it won't work if you have an explicit operator B. If you have an operator B, it will just cast it like it did before. If you only have an explicit operator B, it won't cast it. And then you have to specifically request a cast with a static cast. For bool, this is particularly nice. Because often you had the case that, say, a function takes a bool, and what you're passing in is a pointer. Well, it would automatically say, oh, well, the pointer is either null or non-null, and then just initialize the bool with either true or false, right? But if the bool that you passed into the function was really a misnomer, you were expecting a bool. Or you were, and the function was supposed to be overloaded for pointers, but you just forgot, then it would just get called and you just have a bool sitting there with false or true in it. Now, to prevent these kind of things, the C++ 11 introduces the Boolean context kind of thing. A Boolean context is where something really should be a bool. For example, if statement. If pointer, parentheses. This is you can call my explicit operator bool and turn me into a bool. Because the user, if you're writing if parentheses something, then you are probably assuming that you are expecting the Boolean context. The pointer, null pointer, is supposed to be false and everything else is supposed to be true. So this is a Boolean context. And there are a few things which are actually invoking the Boolean context. The and, the not operator. So if you say A and B, the logical and, the logical or, the logical not, it will actually invoke the explicit operator bool. So if this guy here would only have, that's coming out of that equality, would only have an explicit operator bool, actually invoking the not operator here would be enough, because not operator in front of something is a Boolean context. Okay, that much about C++. Let me see, where's my mouse? And here is my scrolling. Good. So let's carry on a little bit about ranges, and then I will tell you a little bit more about error handling. We already noticed that there is kind of the container versus range idea. We already talked about it kind of implicitly. There are containers in this world, vector string list. They own elements, and they have deep copy semantics. So if you copy them, you actually copy the elements. It usually takes O of n time, because you have to copy all the elements. Where n is the number of elements in your container. And they have deep constness. So if these things, if the element, the object itself is const, if you have a vector constref, then the iterator is going to be a const iterator, and you can only access the elements const. You can't mutate them. Now, this contrasts with ranges. So you have, the only range that we've introduced so far is the iterator range. It references the elements. It has shallow copying. So we've seen that you basically, when you copy, you just copy a reference. You copy the iterators. You don't copy the values that the iterators are pointing to. And you have shallow constness. So if you make the iterator range constref, that doesn't do anything to the constness of your elements. It just depends on the iterator that's inside the iterator range. And these are basically the two types of things that, that both can be iterated over. So they needed a term for that. And they call it a traversable. So a traversable is a range or a container. And you could produce something like a make range that creates a range that spans the whole container. And this is not the same as the container itself, because then when you copy it, for example, you don't copy the container, you only copy the reference. So you can have multiple ranges pointing to the same container inside some function. So there it may make sense to define something, a helper function, make range, that basically just produces an iterator range of your whole container, begin, end, and does nothing else. That's okay. Okay, now this is the last thing I want to talk about, which actually makes these, last thing regarding ranges that I want to talk about, which makes ranges rather interesting. range adapters. This is like the good old world of range find, already taking a range parameter here, and it spits out an iterator. Okay, so you are looking for the 4 inside the vector, and this spits out the iterator where you actually found the 4 inside the vector. Contrast this with that. You have a structure A that contains an int. This vector has an int, is of ints. This structure A has an int. Okay? And we want to do exactly what we are doing here, find the first 4 on that structure. You want to find the first int ID that's 4. And right now you have to write it like that, which is rather ugly. You have to say, oh, range find if, assuming you also have a range version of find if, the vector a const reference, and then return a.id equals 4. Okay? Now, these two things do something similar in one aspect. They are looking for a 4. Now, but they look completely different. It's weird that you have to write these two things so differently just because the int here is stuck inside the structure. You would like to have a similarity in implementation. Now let's see, what do we really want? How could this look like? Like this, for example. You say, oh, my range is first transformed, my V of A's is transformed by projecting it onto AID. Okay, so you're getting all the ints out of the vector, and then this resulting range then runs over ints, and now I want to find the 4 inside that range. And this kind of thing here is is basically the reason why ranges changed your programming so much. Because suddenly you do this stuff a lot. You're transforming a lot. There's also a filter which I'm going to show you. This is really the gist of it. This is what makes it nice. Because suddenly you can break down your problem into the actual logical steps. You don't have to write these monolithic predicates anymore that do two things at the same time. They do the projection, and then they do whatever comparison or whatever you need to do. Okay? So this is what makes it real nice, and that's why I really encourage you to program with ranges instead of iterators. There's a little subtlety here. What's the iterating over? Well, naturally ints, because otherwise you wouldn't be able to find a 4 inside that range. So range is actually, this range is of ints, so you find a 4 and return, and so this it is actually iterating over ints. Okay? Now what if I want to iterate, or if I point to the A instead? Well, usually we have, luckily, with all the nice range libraries out there, ours and boost range and whatever, we have this .base member of the iterators that are coming out of this range. So basically this range still knows, originally I was running over a vector of A's, I just got transformed it, and I can get the original iterator back. And it should be clear by now, this transform, of course, doesn't execute immediately. It's not like when you call this thing here, it actually runs over all the V's, creates a new vector, and with all the ints inside. Right? That's not the point. The point is it's doing that while it's executing. Whenever you are asking star it goes and says, okay, star it. Okay, I have to go to the vector, get the value out, project that value onto the id, look into the id, and return the id. So that's how that thing works. And that's why the .base is still pointing to the original elements of your V. And then you can write it nicely like that. Now, how would you implement such a thing? Let's see. Let's first do it with plain vanilla nice iterators. You have a transform range, and inside the transform range, you have an iterator type, and begin and end will return that iterator type. And what does an iterator type have to do? Well, first of all, it can, when you call base on it, we already saw that. First of all, what does it contain? It contains the functor. Okay, what do you do on the thing that you want to transform? And it also contains the iterator of your base type. So internally, it has like an iterator. This is where I am in my vector, and the functor that every time I take something out of the vector, I have to transform it with my functor. This is here. Okay. And here you can see return decal type R value by value. If this guy produces an R value for whatever reason, we turn it actually into an iterator, into a value. And here we can return by ref. And I'll leave to you to figure out why that is. OK, so these are the two things that we actually have. Now, looking at this, it's a bit ugly. Why? Well, the functor here is inside every iterator. So every time you're doing a begin, you get a copy of the functor. And you do an end, you get a copy of the functor. And if you pass around the iterators and assign them to each other, you copy always the functor. If the functor is really lightweight, maybe that's OK, but it's not really nice. If the functor gets really big, then you get really fat iterators. And then you copy these iterators every time. It's kind of hard, right? So you don't want to. Maybe that's not such a hot idea. But it's not that bad yet. Let's see what we're going to do next. Let's look at the filter adapter. Okay? Now, here we want to have the range of all A with A ID equal 4. Okay? And we could do something like that. Could say, OK, filter my V's. These are now A's. And you filter these with that functor. You say, if 4 is AID, then I want this to be member of my range. Otherwise, not. Okay? So, and this is also lazy, right? While you're walking over your V, you say, is this 4? No. Is this 4? No. Is it 4? Yes. Okay. Here we go. This is your next element. So this is how it's supposed to work. And these two things, filter and transform, with these two, you can already do many things. This is the very basic algorithms in your adapter vocabulary, essentially. Now let's see how the filter adapter is implemented. Oh, it's great. So you have an iterator again inside a filter range, and you got the functor. Yeah, we carry around the functor. That's fine. And we have the iterator. And we have another iterator. Why do we have another iterator here? Well, let's take a look why we have another iterator. So when you are implementing the operator plus plus of your iterator, of this iterator inside the filter range iterator, you have to do the following. You have to step one step forward. And then you have to see, oh, have I reached the end? If I've reached the end, then I'm fine. I will just bail out. Or am I not meeting my filter? If I'm not meeting my filter and I haven't reached the end, I have to keep going forward until I find something that actually hits my filter, meets my filter. Now, why do we have a static bool here? Well, because again, we have a Boolean context, and we want to enforce that this thing mfunc is actually evaluated, whatever it returns, in a Boolean context. I talked about this already. But here you can see, in order to run off the end, you have to carry around the it end. So far, so good. Boost range implements this. Is this a good idea? Let's see. How does the iterator look like? Of range filter, of range filter, of range filter, and so on. The third outside filter has a functor. And it has the iterator. And the iterator has a functor. That functor here. And it has an iterator. And that iterator has a functor. And it has an iterator. And it has the end iterator. And yeah, and this guy also has the end iterator, which again has the functor and the iterator, and the other iterator. Oh, this iterator is end, and this one is also end, because here you are actually, the current iterator of the end iterator is the end iterator, and then you are getting functors, iterators that look like this. And at some point you are copying around 1 kilobyte big iterators. And you are doing this constantly in your loop. Right? And that is a really great idea. And they're doing this in boost range. And they never noticed. And there's our little contribution until we told them. And they will make the standard. I think we've done that much. They will make the standard that this is possible that this won't happen. So this is a little thing we've done. OK, how do we do that? How do we make this not happen? Let's do it more efficiently. We must keep the iterator small. Now, the adapter object carries everything that is common for all iterators. That's the general idea. So if you have a functor, why do we store the functor everywhere? We don't have to store it inside the iterator. We can store it inside the range. Okay? And then our iterators, like the functor we can store there and the itend we can store there. And now the iterators can carry a reference to the adapter object for all the common stuff that they need to access, like the functor and the end. And they can store their own iterator, where am I in my vector? And then everything is good. So every time I increment the iterator, I can ask my range, my filter adapter object, what's the end, what's the functor, and I can do all my work that I need to do. Fantastic. Again, we do the exercise. What does the iterator look like of range filter, range filter, range filter? Range 3, range iterator 1, but this guy can range 2 and iterator 2 and range 1. Yeah, it's better, but it's still linear. You stack this thing, and they still get big. It's ugly. I want to do better. Okay? Always want to do better. Can we do better? Of course we can. Let's introduce the index concept. Okay? What's an index? That's our solution to the problem. Now, an index is kind of like the iterator. But for all its operations, it needs its range. It needs its adapter object, or its range in general. So an index range, which is a range that fulfills the index interface, has some type def that says, OK, this is my index. It has some, oh, give me the begin index, give me the end index. Please increment my index. I give you this index to increment. Please increment it for me. You can decrement it for me, and you can dereference the index. So whenever you want to do something with the index, you have to go to your index range, and it will do it for you. Okay? Now, of course, that's not better than the iterator, because an iterator can do its things by itself. Here, you always need the range. So this is, of course, worse than the iterator. An index is kind of more stupid than the iterator. But maybe it can help us. First of all, we have to find out if we have this interface. Okay, the index range right now doesn't have an iterator. It has an index. That's bad, because we have lots of algorithms out there that all need iterators. And if we say, oh, we're going to throw away all the old stuff, we're going to rewrite the standard, you know what happens, right? Everyone says, no, you can't. Sorry, we've standardized iterators. You must have iterators in your range. It's like, well, that's not a problem. That's all right. You can do that. So first of all, any iterator-based range can be made an index range. Okay? So when you have something that has say a vector or whatever, you can always put an adapter on top of that that says, okay, call your iterator the index, and I'm going to implement the interface for the index range interface. And whenever I say, hey, adapter object, please increment, or hello range, which is then going to be vector, for example, please increment the index, then you know, the index is just my iterator. I just need to increment the iterator. Thank you, I'm done. So this way is pretty trivial. You can always turn an iterator range into an index range just by basically calling your iterators indices. And then just implement the interface. It doesn't take any extra memory or anything else. It's basically just an adapter that you plug into your iterator range, and it will become an index range. It will fulfill the interface of an index range. Now, okay, why do we do all this? Okay, let's write a filter range in the index-based fashion, and see if we have an index-based filter range where we can do this efficiently. The increment index looks like this. You're getting the index. First of all, you are storing inside the filter range, as before, a functor. You don't store the end iterator. Instead, you store a reference to your base range. Okay? And you assume that the base range is also an index range. This fulfills the index interface. Well, what if you get a vector and you're asked to filter a vector? Well, as I said, you can always say, are you already an index interface? Do you have the index interface? No. Okay, then I slap on this adapter and say, okay, now you're going to behave like an index interface. It's all going to be fine. So you can assume that basically what you're storing here is fulfilling the index interface. Then you say, okay, increment index. Oh, what's my index? The index actually happens to be the index of the base. And now you see where this is going to. Because really, if you have, and see whether this works, right? So you say, okay, the base index is the same, the index is the same as the index of my base range. I don't have to add anything to that index when I filter it. I just adopt it as it is. And then I say, okay, can I increment it? Can I actually write the interface? Okay, I increment index of index. Well, I just ask the base range to increment the index for me. Because, I mean, this is the base index. It's the same type. I can ask the base range to increment it for me. And I can do that until I hit the end index of my base, or until I have something that fulfills my filter predicate. And again, for the dereferencing, I again forward this thing to my base. So I can always, since my index is just like the index of the base, I can always ask my base to do stuff for me. It's all good. I can do it. And now you are basically implementing the filter range and the transform range you can also do. And very much the same way. Most of the time, this index here is going to stay unchanged when you are filtering or transforming things. Notionally, all this is the position in the vector. At the very bottom, after you unroll the whole stack, you're going to have a gazillion stack. At the end, it's just like, okay, where am I? Here. Okay, so this is just an iterator of a vector. And everything else you can implement by referring to your stack of bases. Now, you say, well, we still have, which is great that we have like a filter range that's based on indices, right? But the standards committee is going to come to me and say, you can't do this. You must provide iterators because all the algorithms are written in terms of iterators. Right? You can't indices that's a newfangled thing, and then you're not going to support it, right? Well, luckily, we can actually write an iterator for it. It's so easy, right? All the iterator needs is a pointer to its range. Again, pointer, not reference, because you want to make this thing assignable. And you actually also store the index. You store a pointer to the range and the index. And when you are asked to please increment yourself, you just ask your range to increment yourself. And this is completely generic. This is the same way for every index range. You just always forward to your range. It's all fine. And it doesn't matter whether that's a transform range, a filter range, blah, 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 whatever. Whenever you have an index range, you can make an iterator for it that way. Now, all the iterators are 2 pointers, no more. Doesn't matter how big your stack is. You always have 2 lightweight iterators that have the size of 2 pointers. Already when we made the first improvement, the lifetime of the range iterator, where we stored stuff inside the range object, we already made the assumption that we have to, the iterators of the adapter are only going to live as long as the range. Because as long as when the iterator is pointing to the range, you can't pull the range out under the feet of the iterator. Can't do anything anymore. It'll point to uninitialized memory. Doesn't work. Okay, so that is the restriction you are getting. But it looks like this is also the requirement we have. We said basically, we stood up and said, please don't standardize a range library that allows the iterators, or that requires that the iterators outlive the range. If you standardize that, and if you pour that into concrete, the world's going to be bad forever. So, and I think they understood that. They won't do it. Maybe they won't standardize the index for now, which isn't bad. You can always use that optimization and still adhere to the standard, as long as the standard requires that your ranges, your iterators can't outlive their ranges. That is the important requirement that they will put into the standard, and it looks like they will put this into the standard. Okay, one last thing about ranges, subranges. And I don't know if they're going to put this into the standard. I think if they don't, they're going to get hurt. Example. You have, what's a subrange? Well, the subrange is kind of like a part of a range, of a vector. It's kind of like an iterator range, except that now we don't really play in iterators anymore. We play in indices. Okay, we don't, all iterator is all old school. And we now want to do indices and the base range. And if you count the number of pointers, 1, 2, 3, say this is a vector, this is a pointer, pointer, pointer. We have 3 pointers. Before, when we are storing iterators, we would have 4. So there, it's maybe better to store indices. Okay, now, again, we generate our iterator with our generic iterator for index facility that turns that index stuff into iterators. Now we use this thing. This is basically what's being returned for something like slice. Right? We have a little function that says take this vector and give me a range that goes from the 2nd element to the 4th element. And this is then of type subrange std vector int. Okay. Now, functions like head and tail are probably also practical, where you say, okay, give me up to that element or after that element. It's kind of the things that you know out of functional programming languages. It's quite common. And we're going to have that in the range library as well. Okay, now let's say equal range will return such a thing, right? What does equal range do? Well, it basically says, as the name suggests, if this is a range and the range is sorted and you give it a value, it gives you the range of values that have that the range of elements that have that value. So you have somewhere like a 3, 3, 3, 3, 3, and you do an equal range of 3, then you get this back. Now, this is the same as lower bound to upper bound, to functions that you may be familiar with, that are also in the standard library. Now, naively, you should be able to write something like this. A lower bound is defined as the range begin of the equal range. You probably wouldn't implement it that way because maybe it's inefficient, but similar code may appear in user code, and it's quite reasonable to be able to write something like that. You get a range back, it goes from here to there, well, just take this and return it. Does this work? Remember what I said about the lifetime of iterators. Ouch. This returns a range. This returns an iterator to this range. The iterator survives as a return value of lower bound. The range goes dead. You have undefined behavior. This iterator points to places that are not there anymore. Okay. That's bad. You may also want to do something like this, much more directly. And maybe this actually points us to the direction of a solution. You take range begin of range, that's an iterator, and that's a place kind of semantically, that's why I'm saying put on the philosophical glasses. This points us to a place inside range. Now what does this point us to? Well, this is range equal range, range. Range begin of this is a place inside range. Goes from, the 3's go from here to there. The whole thing goes from here to there. Well, this is just a position, just as much a position as that one. And this is a position at the end as well. So you should be able to do this. You should be able to say, okay, I have a type here, auto it, and now I want to assign a different place to this it, which just happens to be coming from the equal range begin. And you should be able to assign it here. Why not? Right? This is a place in my range. And it's all just places. Why worry? And it's kind of hard to come up with a similar example for the transform range. There, you don't have that kind of thing where here it comes out a transform range and you are expecting that you can assign it to something that is equal to the begin, right? Because what you are getting back from a transform is something that iterates over a different kind of values. I mean, naturally you can't assign it to something that iterates over like the thing that iterates over ints, you assign to something that iterates over a's, for example. That's kind of expected that doesn't work. But here, this should work. And this points us to the fact, again, we believe, we as ThinkCell, subranges are special. Subranges should not follow this into the footsteps of filter and transform. The subrange iterator type should be equal to the range iterator type. And that's kind of what, anything else is not practical. There are libraries out there that do it differently, and I think they're mistaken. OK. Well, if you want to do this, and if you want to implement this as an index range, you need a little bit of an addition here to your index interface. You basically need to be able to tell your base range, hey, can you make an iterator for me with your index? This is your index. This is you. This is your index. Could you turn this into an iterator for me? Thank you. Yeah, OK, then I can return it here. This is an additional facility that you need, which is based on the so you have to have some sort of make iterator function, which is quite natural to have. I mean, if you have the index range, and the index range should be compatible with iterators, then this is a quite natural function to have. OK, I want to stop here regarding ranges. I think I covered the most important facilities, in particular the facilities that are most important regarding programming. You will love the transform and the filter. I'm going to have the URL of our range library. There's boost range, which for all practical purposes, yeah, it can be used, and you can already get used to kind of using ranges. Forget about iterators. Iterators are old school. Use them where appropriate, but kind of like iterator pairs and things like that, well, don't use that anymore. It makes for hard to read code, and we found it very, very useful to do lots of things with ranges.